Hello everyone. Tonight we dive deep into why everything we know about time is wrong. Now, dim the lights and let's ease into tonight's journey together. Imagine waking up one morning to discover that time had stopped. Not the ticking of a clock, but time itself. You walk through your house, but nothing moves. Raindrops hang motionless in the air, and even your own footsteps make no sound. This sounds like a scene from a science fiction movie, but in a way, it's closer to reality than you might think. Because time, as we understand it, may not be as absolute, linear, or reliable as our daily lives suggest. In this documentary, we're going to dive deep into the strange and wondrous nature of time, a force so intimately tied to our existence, yet still wildly misunderstood. To begin unraveling this mystery, we must first address a basic assumption: that time flows. We often imagine time as a river, constantly moving forward, never back. This idea is baked into our language. We speak of moving through time, of running out of time, of turning back time. But in physics, especially at the level of fundamental laws, time doesn't really flow at all. In fact, most of the fundamental equations describing the universe are time symmetric. That means they work just as well, whether time runs forward or backward. This is one of the most profound puzzles in modern physics. If the laws of the universe don't care about the direction of time, why do we? Why do we remember the past and not the future? Why does a broken glass stay broken and not reassemble itself spontaneously? The key to this question lies in entropy, a concept from thermodynamics that measures the amount of disorder in a system. In any closed system, entropy tends to increase. This is the famous arrow of time, which gives us our sense of past, present, and future. A clean room becomes messy, not the other way around. Heat flows from hot to cold. The universe moves from order to disorder. But this is not because the laws of physics demand it. It's because of probability. There are far more disordered states than ordered ones, so it's statistically likely we'll see things become messier over time. However, entropy doesn't explain everything. It doesn't tell us what time is, only how systems change within it. To go further, we need to leave Earth behind and look at time from the cosmic perspective. According to Einstein's theory of relativity, time is not a universal constant. It is woven together with space to form a four-dimensional fabric called space-time. And this fabric bends and stretches in the presence of mass and energy. In other words, gravity can slow down time. This has been proven through experiments with incredibly precise atomic clocks. A clock at the top of a mountain ticks slightly faster than one at sea level because it's farther from Earth's gravitational pull. This effect is called gravitational time dilation, and it's not just theoretical, it's built into your phone. The GPS satellites orbiting Earth have to account for these time differences, so your location remains accurate. Without correcting for gravitational time dilation, your phone's map would be off by several kilometers in just a single day. But it gets even weirder. If you were to approach the event horizon of a black hole, time for you would slow to a crawl relative to someone farther away. If you managed to hover just outside the event horizon and then escape back to Earth, you might find that while only a few hours had passed for you, years, or even centuries, had passed for everyone else. This isn't science fiction. This is time as it really behaves near extreme gravitational objects. And it means that your experience of time depends entirely on where you are and how fast you're moving. In fact, movement itself affects time. According to special relativity, the faster you travel, the slower time moves for you compared to someone standing still. This effect, called time dilation, has also been measured experimentally with particles moving near the speed of light in particle accelerators. These particles decay more slowly than they would at rest, essentially experiencing less time. If you were to board a spaceship and travel at near light speeds to a distant star, you might return to Earth having aged just a few years, while decades passed for those who stayed behind. This is the famous twin paradox, and it has real scientific backing. Time, in this sense, is not absolute. It bends to motion and gravity. This revelation shatters our everyday assumptions. Time is not a single, universal river. It's more like a vast ocean, with currents, eddies, and whirlpools flowing at different speeds in different regions. What you call now might not exist in the same way for someone else in another part of the universe. And then there's quantum mechanics, a world where the nature of time becomes even more bewildering. At the smallest scales of reality, particles can exist in superpositions of states, being here and there, spinning this way and that, until observed. But when does this observation happen? What causes the collapse of a quantum state into a definite outcome? Time in the quantum world doesn't behave the way it does in classical physics. Some interpretations even suggest that the future can influence the past, a concept known as retrocausality. And then there's the question of whether time even exists at all. Some physicists propose that time is an emergent property, something that arises out of deeper, timeless laws of physics. According to these ideas, time as we know it might be an illusion, a useful construct created by our brains to make sense of changes in the universe. In fact, when we look at the equations of string theory, loop quantum gravity, or other theories of quantum gravity, time often disappears altogether. The universe, at its most fundamental level, may be timeless, and the flow of time a byproduct of our limited human perception. So where does that leave us? It leaves us with a puzzle, a universe that behaves differently than we expect, where clocks tick at different rates, where time can slow, warp, and possibly even disappear entirely. And yet, in our daily lives, time feels so real, so rigid, so unstoppable. In the next section, we'll journey deeper into the mystery of relativity and space-time, exploring how Einstein's radical ideas reshape not only our understanding of gravity, but time itself. Because if we are to truly grasp why time doesn't work the way we think, we need to explore the very fabric of the cosmos, and how it changes everything we knew about past, present, and future. In the early 20th century, a young patent clerk named Einstein proposed something that shook the foundations of how we understand the universe. Time, he said, is not separate from space. Instead, the two are bound together in a single, unified entity, space-time. This idea, radical at the time, became the backbone of modern physics. But while most people have heard of relativity, few truly grasp what it means, and even fewer realize how deeply it challenges our intuition about time. Einstein's insight came in two stages. The first, special relativity, dealt with the relationship between time and the second, general relativity, extended those ideas into gravity and acceleration. Let's start with special relativity. Imagine you're on a train moving at a constant speed. A beam of light is emitted from the center of the car, traveling toward both ends. From your perspective on the train, the light hits both ends at the same time. But to someone standing outside the train, the back of the train is moving toward the light beam, while the front is moving away. To this stationary observer, the beam reaches the back before the front. This thought experiment reveals a startling truth. Simultaneity is relative. Two events that seem to happen at the same time for one observer may not be simultaneous for another. That means the notion of a universal now, a single shared present moment, doesn't exist in the universe. Your now is not necessarily the same as someone else's now, but this also implies something more profound, that time can stretch or compress depending on how fast you're moving. As your speed approaches the speed of light, time slows down for you compared to someone at rest. This is not a mere illusion or trick of measurement, it's real. Time actually passes more slowly for fast-moving observers. This is time dilation, and it has been confirmed in multiple experiments. For example, muons, unstable subatomic particles produced when cosmic rays strike Earth's atmosphere, decay in microseconds. But because they move at near light speeds, time dilates for them. They survive long enough to be detected at the Earth's surface. Without time dilation, they'd never make it that far. Even more dramatic evidence comes from atomic clocks flown on aircraft or satellites. These clocks, traveling at high speeds and experiencing different gravitational conditions, fall out of sync with identical clocks on Earth. This isn't a malfunction, it's relativity in action. Now let's step into Einstein's second theory, general relativity. If special relativity showed us that time is relative to speed, general relativity revealed that time is also affected by gravity. The greater the gravitational field, the slower time runs. This effect is so precise that GPS satellites orbiting Earth must adjust for it to remain accurate. Think about that. Your phone, something you use every day, functions correctly only because scientists understand how gravity warps time. Without this correction, your location could be off by miles in just a few hours. So what does it mean that gravity slows time? Picture space-time as a stretched rubber sheet. A massive object like Earth or the Sun creates a depression in this sheet. Objects move along the curves and slopes caused by this depression. This is gravity. But it's not just space that gets distorted. Time does too. Near a massive object, time ticks more slowly. This isn't noticeable in everyday life, but it becomes dramatic near something like a black hole. There, gravity is so intense that time nearly stops at the event horizon, the boundary beyond which nothing, not even light, can escape. Imagine an astronaut falling into a black hole while their friend watches from a distance. To the observer, the astronaut appears to slow down as they approach the event horizon, eventually freezing in place. But to the astronaut, time feels normal as they fall inward, possibly experiencing only minutes, while billions of years pass outside. This kind of time distortion, though extreme, is not hypothetical. It's built into the equations of general relativity, and it challenges our basic assumption that time is uniform everywhere. In truth, the universe is a patchwork of time zones, each ticking at its own pace depending on local gravity and velocity. But here's where it gets even stranger. If time can bend, stretch, and slow, could it also reverse? This question has haunted physicists for decades. As mentioned earlier, the fundamental laws of physics don't care whether time moves forward or backward. The equations work either way. But our universe does seem to prefer one direction, forward. We call this the arrow of time, and it appears tied to entropy, the tendency for systems to move from order to disorder. Still, some theories suggest that under the right conditions, time might not be so one-directional. Certain solutions to Einstein's equations allow for closed time-like curves, paths through space-time that loop back on themselves. In theory, if you could travel along such a curve, you might return to your own past. This is the basis for many time travel theories, and while highly speculative, it is not ruled out by the math. Of course, time travel brings with it a host of paradoxes. The most famous is the grandfather paradox. What happens if you go back in time and prevent your grandfather from meeting your grandmother? Would you cease to exist? Or would the timeline split into alternate realities? Some physicists think these paradoxes prove that backward time travel is impossible. Others believe that if it ever were possible, the universe would find a way to maintain consistency, what's known as the Novikov self-consistency principle. Still others invoke the multiverse. Maybe changing the past simply creates a new timeline, branching off from the original. These are wild ideas, but they reflect the deep uncertainty we still face when trying to understand time. We've built machines that measure it with nanosecond precision. We've developed theories that describe how it bends and slows. Yet the essence of what time is remains elusive. Is time fundamental, or is it an emergent property, something that arises only in certain conditions, like temperature? Could time be a side effect of consciousness, or of entropy, or of something else we haven't even discovered yet? In upcoming sections, we'll explore these questions in greater detail. we'll dive into the weird world of quantum mechanics, where particles can influence each other across time. We'll look at the possibility of timeless physics and the implications of theories like loop quantum gravity. And we'll consider what it means for time to end, a question with real consequences for the future of the universe. Because if we hope to truly understand time, we must look beyond the ticking of clocks and calendars and into the deepest structure of reality itself. At first glance, quantum mechanics and time might seem unrelated. After all, quantum theory deals with the microscopic world of particles, while time, as we experience it, flows across the grand canvas of life. But when you dig deeper, the relationship between quantum mechanics and time is anything but straightforward. In fact, it may be the key to unlocking a much deeper truth, that time, as we perceive it, may not even exist in the way we think. Let's start by revisiting the strange behavior of particles at the quantum level. In classical physics, objects follow predictable paths. A baseball thrown into the air moves in a smooth arc, and we can calculate its position at any moment. But in the quantum world, particles like electrons and photons don't follow such clean trajectories. Instead, they exist in a superposition of states, simultaneously occupying multiple positions or spin states, until observed or measured. This collapse of the wave function, where a particle's probability cloud suddenly snaps into a single, definite state, raises a troubling question. When, exactly, does this happen? What counts as a measurement? And perhaps most puzzling of all, does time play a role in this process? Some interpretations of quantum mechanics, like the Copenhagen interpretation, sidestep the question entirely. They simply say that observation causes the wave function to collapse, without elaborating on how or why. But others go further, suggesting that the act of measurement is not just a moment in time, but a fundamental disruption in the nature of reality. Take the delayed choice experiment, for example. This is a variation of the famous double-slit experiment, where particles are fired one at a time through two slits and then detected on a screen. If you don't observe which slit the particle goes through, it behaves like a wave, interfering with itself and forming a distinctive interference pattern. But if you observe which slit it goes through, it behaves like a particle, and the interference disappears. Now, in the delayed choice version, the decision to observe the particle is made after it has already passed through the slits. Remarkably, the experiment still works. The particle seems to retroactively decide whether to behave like a wave or a particle after the event. This implies that events in the present can influence outcomes in the past. This is not just a mind-bending paradox, it's a serious challenge to our understanding of causality and time itself. In classical thinking, causes precede effects, but in the quantum realm, the line between past and future begins to blur. Some interpretations, like the transactional interpretation, even propose that quantum interactions involve a kind of handshake between past and future waves, suggesting that time is not a one-way street, but a bidirectional framework in which information can flow both ways. This brings us to the concept of retrocausality, the idea that future events can affect the past. Though controversial, retrocausality is not ruled out by quantum mechanics, and in some formulations of quantum field theory, it appears as a mathematical consequence. It doesn't mean you can go back and stop a meteor from hitting Earth, but it does suggest that our neat, linear concept of time may be an illusion born of our limited perspective. So what is time doing at the quantum level? One possibility is that it isn't fundamental at all. In quantum gravity, where physicists attempt to unite Einstein's theory of relativity with quantum mechanics, time often disappears from the equations entirely. The Wheeler-DeWitt equation, a central equation in quantum cosmology, describes the quantum state of the entire universe without any reference to time. It's static. This has led some physicists, like Carlo Rovelli, to suggest that time is emergent. That is, it arises only in specific conditions and from interactions between subsystems. In his theory of relational quantum mechanics, time doesn't exist on its own. Instead, it's a relationship between events or changes in state. Nothing moves through time. Rather, things change. And from those changes, we infer the passage of time. Imagine a book with every page showing a still frame of a movie. To us, the book is timeless. It just exists. But if we flip through the pages, we perceive motion and progression. Time, in this analogy, is not part of the book. It's something we impose through observation and memory. Another possibility comes from the concept of entanglement. When two particles become entangled, their properties are linked, no matter how far apart they are. Changing one seems to instantly affect the other, even across light years. This instantaneous connection suggests that information is being shared outside of conventional time and space. Some researchers propose that entanglement may be the true foundation of time itself, that the way systems become entangled and then decohere, lose their quantum correlations with one another, creates the illusion of time passing. In this view, time might not be a physical dimension at all, but a statistical trend in how quantum information flows through the universe. It's a mind-bending idea, but it aligns with the strange results of quantum experiments. The further down we go into the fabric of reality, the less solid time becomes. What we call the arrow of time might just be the direction in which information spreads and correlations fade. And yet, despite all of this, we still live in a world where we age, where memories accumulate, where cause and effect rule our decisions. So how do we reconcile our lived experience with a quantum reality where time is fuzzy, fluid, or even non-existent? Some philosophers and physicists suggest that consciousness plays a central role in this, that our minds, designed to survive and make sense of the physical world, are wired to perceive time in a linear, causal way. Our brains stitch together the flow of moments into a coherent narrative, just as they stitch together still images into a sense of motion. But that doesn't mean time is truly flowing. It may mean we're riding along a track already laid down in the structure of space-time, what some call the block universe. In this model, the past, present, and future all coexist like different places on a map. Our perception of moving through time is akin to reading a story page by page, even though the entire story already exists. If this is true, then your birth, your current moment, and your death are not separate events unfolding. They are coordinates on the timeline of your life, all equally real and permanent. In this sense, you don't move through time. Your consciousness simply experiences one frame at a time. Quantum mechanics doesn't give us a final answer, but it shows us just how fragile and peculiar our concept of time really is. It challenges the illusion that time flows, that the future is unwritten, and that causality is absolute. And it invites us to think differently, not just about physics, but about existence itself. In the next part, we'll explore the thermodynamic arrow of time, the reason why eggs don't uncrack, and why time seems to flow in one direction, despite the laws of physics being reversible. Because as strange as quantum time may be, entropy and disorder offer a different, equally strange story about why the universe moves from past to future. Why does time seem to flow in one direction? Why do we remember the past but not the future? Why does your cup of coffee cool down but never spontaneously heat up? Why do you grow older and never younger? These questions might seem like common sense. After all, that's just how life works. But physics says otherwise. The fundamental laws that govern particles, forces, and motion are, with very few exceptions, time symmetric. That means they don't care whether time is moving forward or backward. The equations work just as well in reverse. So why doesn't the universe behave that way? The answer, or at least a very compelling one, lies in entropy, a concept at the heart of thermodynamics. Entropy is often misunderstood as disorder, but a better way to think about it is this. Entropy measures the number of microscopic configurations that a system can have while still appearing the same macroscopically. The more possibilities, the higher the entropy. Let's break that down with an example. Imagine you walk into a kid's room and it's perfectly clean. Every toy is in its place. There are only a handful of ways all those toys can be arranged to produce this tidy state. But after an afternoon of play, the toys are everywhere. The room looks messy, and there are millions of ways those toys could be scattered. That messy room has high entropy, and crucially, it's far more likely to occur simply due to probability. This is the second law of thermodynamics. In a closed system, entropy tends to increase. It's not a law based on physical forces, but on statistics. There are vastly more high entropy, disordered states than low entropy, ordered ones. So, over time, systems naturally drift toward higher entropy, not because something pushes them, but because there are more ways to be disordered than ordered. This statistical drift gives us the thermodynamic arrow of time, the reason we see cause followed by effect, heat flowing from hot to cold, eggs breaking but never unbreaking. It's the only arrow in physics that distinguishes the past from the future. But here's where things get strange. If entropy defines the arrow of time, then why was the universe's entropy so low at the Big Bang? You'd expect that the early universe, a hot, dense, chaotic fireball, would have had extremely high entropy. But cosmologists have found the opposite. Despite being filled with energy and radiation, the early universe was in a surprisingly ordered, low entropy state, particularly in terms of its gravitational configuration. Matter was evenly spread out, and gravity had not yet clumped things into stars, galaxies, or black holes, which are extremely high entropy objects. So why did the universe begin in such a state? This question remains one of the biggest unsolved mysteries in physics. Some suggest it was a kind of boundary condition, that the universe simply started that way. Others believe there may be deeper physical laws that required it. But regardless of the cause, this low entropy beginning is what allows time to have direction. It set the stage for entropy to increase, and for time, as we experience it, to move forward. This concept has profound implications. If the arrow of time is tied to entropy, then time itself is not a fundamental aspect of reality. It's an emergent one. Without a low entropy beginning, there would be no time's arrow, no past and future, no memory or aging, just a static, timeless configuration of the universe. This idea that time is a result of entropy also raises fascinating questions about the future. Will entropy ever stop increasing? What happens when the universe reaches maximum entropy, a state called heat death? In the far future, assuming no unknown forces intervene, the universe will become increasingly uniform. Stars will burn out, matter will decay, black holes will evaporate via Hawking radiation. Eventually, the universe will reach a state of thermal equilibrium, a bland, featureless expanse where no further work or change is possible. This is the so-called heat death, and it represents the highest entropy state possible. In such a universe, there would be no events, no change, and, if our current understanding is correct, no time. Because if time is the measure of change and entropy no longer increases, time effectively ends. But this projection relies on the assumption that entropy will always increase. What if that assumption breaks down? There are speculative theories that suggest entropy might decrease again under certain cosmic conditions. One controversial idea posits that the universe could undergo a big crunch, collapsing in on itself. Some have argued that if entropy reversed during the collapse, then time might reverse too. Events would appear to run backward. You would unage. The future would become the past. This is purely theoretical, and there's no current evidence that such a reversal is occurring, or could. But it illustrates just how intertwined entropy and time are. They are two sides of the same coin. If one changes direction, so does the other. Even in more grounded discussions, entropy affects how we understand consciousness, memory, and causality. Your memory of the past is essentially a record of lower entropy states. Brains, like all biological systems, are low entropy islands that temporarily resist the larger trend of increasing disorder. But even they must eventually yield to entropy. This paints a poignant picture. The reason you can remember the past but not the future is that memories are built by increasing entropy, by burning energy, altering chemical states, and recording changes. The future hasn't happened yet, not because it doesn't exist, but because entropy hasn't created it yet. It also recontextualizes death. Organisms are highly ordered systems fighting against entropy through metabolism, repair, and replication. But eventually, the tide of disorder wins. Cells break down. Complexity unravels. Life returns to entropy. Time, in this sense, is not just a backdrop. It's the very process of things falling apart. Yet there is beauty in this. Stars form, shine, and die because of entropy. Galaxies swirl and evolve because of entropy. Your thoughts, your dreams, your experiences, all of them are embedded in this entropic process, carried along by time's irreversible march. In the next section, we'll return to relativity and explore one of its most stunning implications, the concept of the block universe. What if past, present, and future all exist at once, and time is not a flow, but a frozen landscape of events? What if everything that has ever happened, and will ever happen, already exists? Not as memories, not as predictions, but as real, fixed points in a vast, unchanging structure. This is the central idea behind the block universe, a concept born from Einstein's theory of relativity, and it might be the most counterintuitive and awe-inspiring way to look at time. To understand the block universe, let's return to one of relativity's most crucial insights. Simultaneity is relative. As we discussed earlier, two events that are simultaneous for one observer may not be for another. If you're moving quickly relative to someone else, your perception of what counts as now changes. That fact breaks the idea of a universal present. There is no single, absolute moment that defines now for the whole universe. What's present for you might be in the future for someone else, and vice versa. This undermines the notion of time as a flowing river, where everyone floats together through a single present moment. Instead, relativity suggests that all moments, past, present, and future, coexist. They're all equally real. They form a four-dimensional structure called space-time, with time treated as a dimension much like the three dimensions of space. If space is like the length, width, and height of a building, time is the fourth dimension that gives the structure its shape. This is the essence of the block universe, also called eternalism. In this model, the universe is a static, four-dimensional block. Every event, your birth, your first day of school, the moment you read this sentence, and the end of the universe, is already there, frozen into the fabric of space-time. We don't move through time. There is no flow. Rather, we exist at a specific location in the block, much like being at a certain point in a city. Just as you can't say one street is more real than another, you can't say that one moment in time is more real than another. All of them exist. We just experience them sequentially, like watching frames of a movie. Einstein himself hinted at this idea. In a letter to the family of a deceased friend, he wrote, "For us believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion." Coming from the man who reshaped our understanding of time, that statement is profound. But how do we square this idea with our lived experience? If all of time already exists, why does it feel like we're moving through it? The answer may lie in consciousness. Our brains process information in a way that builds the illusion of temporal flow. We perceive events in succession, we form memories of what has passed, and we anticipate what's coming. These cognitive structures may give rise to the feeling of a now that advances forward. But in the block universe, this movement is a perceptual trick. The future isn't something that's being created, it's something that already is, waiting to be experienced. You, at age 10, still exist in that moment. You, at age 80, already exist as well. Just not in the part of the block your current consciousness is observing. This raises fascinating and uncomfortable questions about free will. If all events are fixed in the block, is everything predetermined? Are your choices already etched into the structure of the universe, waiting to play out like scenes in a film? Some argue yes. If the future exists, then it cannot be changed. It's already part of the fabric. Others suggest that while the block universe may appear static, it could still allow for a kind of soft determinism, where outcomes are constrained but not completely fixed. In other words, some future events may be probabilistic, not definite. Quantum mechanics adds another layer of complexity. As we've seen, particles exist in multiple states until measured. Does the block universe include all possible quantum outcomes, or does it select only one branch of reality? Some physicists have proposed combining the block universe with the many worlds interpretation of quantum mechanics. In this version, every possible outcome of every quantum event spawns a new branch in a vast multiverse, a cosmic tree of infinite timelines. Each branch is its own block universe, complete and unchanging, containing every event from beginning to end. It's a staggering vision, an infinite number of timeless realities, each one containing every moment of every life, spread across a multi-dimensional landscape. Whether or not this is true, the block universe model gives us a new perspective on death and loss. If the past still exists, and always will, then those we've lost are not gone. Their moments are preserved forever in the fabric of space-time. The laughter you shared with a friend, the sound of your parents' voice, a child's first steps, all of it is still there, as real as this moment. Of course, we can't access those moments. We are confined to a narrow window of awareness that moves forward, or seems to. But understanding that these moments still exist, and that time itself may not flow, can be both comforting and humbling. It also forces us to rethink causality. In the block universe, cause and effect are not processes that unfold. They are relationships between events. The cause doesn't precede the effect in time. It's simply located earlier in the block. The effect isn't caused in the sense of a push. It's just there, in its place, connected by the laws of physics. In this view, the universe is less like a machine grinding forward and more like a sculpture, timeless, complete, and interconnected. Our experience of change, motion, and choice is how consciousness navigates that sculpture. But the sculpture itself is silent, still, and whole. This doesn't mean time is meaningless. It's still a coordinate we use to describe relationships between events. It's still the framework within which everything occurs. But it's not flowing. It's not passing us by. It simply is. In the next part, we'll explore how scientists attempt to reconcile time with the very beginning of everything, the Big Bang. Because if time is part of the universe, then what came before time? Or does that question even make sense? Time begins with the Big Bang, or so we're told. But what does that actually mean? Did time really have a beginning? And if so, what came before it? These aren't just philosophical questions. They cut to the core of physics, cosmology, and our understanding of the universe itself. Let's begin with what the Big Bang theory actually says. Contrary to popular belief, the Big Bang wasn't an explosion in space. It was an expansion of space itself. About 13.8 billion years ago, the observable universe was compressed into an incredibly hot, dense state, a singularity of infinite density and curvature. From this point, space began to expand. Galaxies moved apart, the cosmos cooled, and over billions of years, stars, planets, and life emerged. But here's the twist. Time itself was part of that expansion. According to Einstein's general relativity, space and time are not separate entities. They are interwoven into a single continuum, space-time. That means if the Big Bang was the origin of space, it was also the origin of time. There was no before, not because nothing happened, but because before is a temporal concept, and time itself hadn't yet come into being. It's similar to asking, what's north of the North Pole? It's not that there's some mysterious land there, it's that the question breaks down. The North Pole is the northernmost point on Earth. Likewise, the Big Bang may represent the furthest we can go back in time. Time, as a dimension, might not extend past that point. This idea is backed by our best models of cosmology. The equations of general relativity allow us to rewind the cosmic clock to a fraction of a second after the Big Bang. But when we push further, to time zero, the math breaks down. We hit a singularity, a point where density becomes infinite and our physical laws stop working. Singularities aren't necessarily real things, they're often signals that a theory has reached its limits. And many physicists believe that at the Big Bang, general relativity simply gives way to something deeper, a quantum theory of gravity that we haven't fully discovered yet. Enter the field of quantum cosmology. Here, researchers attempt to describe the origin of the universe using quantum mechanics, and the results are nothing short of bizarre. One of the most famous models is the Hartle-Hawking no-boundary proposal, developed by physicists James Hartle and Stephen Hawking. In this model, the universe doesn't have a singular beginning. Instead, time itself becomes rounded off at the earliest moments, transitioning smoothly from a kind of imaginary time to real, measurable time. Imagine a sphere. There's no edge, no beginning point, just smooth, curved surface. The Hartle-Hawking model proposes that the universe began not from a sharp point, but from a kind of four-dimensional south pole, where time as we know it simply didn't exist. Asking what came before, that is like asking what's south of the South Pole. In this view, the universe had no boundary, no initial moment of creation. Time simply emerged as the universe expanded and cooled. This suggests that time, like temperature or pressure, is an emergent property of the cosmos, not a fundamental aspect of reality, but something that arises under the right conditions. Other models propose even more exotic origins. Some suggest that the Big Bang was not the beginning of time, but a bounce, a transition from a previous collapsing universe into our current expanding one. These cyclic or ekpyrotic models imagine time stretching infinitely in both directions, with endless universes born and reborn in a cosmic cycle. Still others explore the idea of a quantum foam, a frothy sea of tiny, constantly fluctuating energy fields that bubble with short-lived universes. In this framework, our universe may have emerged from a random quantum fluctuation. Time, in this picture, is just a local condition, a side effect of one particular patch of reality achieving stability. What these theories have in common is the suggestion that time is not a fundamental backdrop upon which the universe plays out. Instead, time may be a product of the universe. In the earliest moments, or beyond the boundaries of our observable reality, time may not exist in any meaningful way. This raises deep questions about causality. If time didn't exist before the Big Bang, what caused the universe to appear? Can there even be such a thing as cause without time? Some physicists argue that asking why the universe began is meaningless without time to define cause and effect. Others speculate that causality could exist in some timeless form, perhaps as part of a higher dimensional framework we can't yet perceive. Philosophers and theologians have also wrestled with these questions. For centuries, thinkers debated whether time was infinite or had a beginning. In the Middle Ages, theologians like Augustine proposed that time began with creation, that God didn't exist in time but created it. Remarkably, modern cosmology is now entertaining similar ideas, though framed in scientific rather than metaphysical terms. Whether time had a beginning or stretches into eternity remains one of the most profound questions we can ask. But one thing is clear: the closer we get to the origin of the universe, the less reliable our conventional understanding of time becomes. Our seconds and minutes, our calendars and clocks, are tools shaped by the needs of life on Earth. They serve us well here. But in the realm of the early universe, of singularities, quantum fields, and dimensional curvature, those tools break down. Time, in the deepest sense, may be an emergent illusion arising from the quantum birth of the cosmos itself. In the next part, we'll journey through time from a cosmic perspective, examining how time has changed since the Big Bang and how it might behave in the distant future. Because just as the universe evolves, so too does time, slower, faster, and stranger than we ever imagined. Let's take a step back, way back, and look at time not from a human perspective, but from the universe's. Time, like everything else in cosmology, has evolved. From the chaotic fireball of the early universe to the cold, stretched out void of the distant future. Time has expanded, cooled, and warped alongside the cosmos itself. At the moment of the Big Bang, 13.8 billion years ago, the universe was unimaginably dense and hot. Particles zipped around at near light speeds in a sea of radiation. Time, as we understand it, was running at a very different pace than it is today. But what does it mean to say that time was different? To understand that, we have to revisit Einstein once again. According to general relativity, time is affected by both velocity and gravity. In the early universe, both of these were extreme. The energy density of space was incredibly high. Gravitational fields were immensely strong. That means time, if it existed in any classical sense, was ticking much more slowly by our modern standards. But here's where things get fascinating. As the universe expanded, the density dropped, space stretched, gravity weakened, and with that expansion, time itself began to unfold. You could say that time was being built layer by layer, moment by moment, as the universe grew in size and complexity. This isn't just metaphorical. In inflation theory, a leading model of the early universe, the cosmos underwent a period of exponential expansion within a tiny fraction of a second. During this phase, time behaved in profoundly non-intuitive ways. Entire galaxies' worth of space were inflated from quantum fluctuations in less than a trillionth of a second. Once inflation ended, the universe continued expanding, though at a slower rate. Matter cooled enough to allow protons and electrons to combine into hydrogen atoms, a moment called recombination, about 380,000 years after the Big Bang. Light was finally able to travel freely through space, and that light, the cosmic microwave background, still echoes through the universe today. From that point on, time started to take on the form we recognize. Cause and effect, radiation cooling, stars forming, galaxies swirling. But even then, the tempo of cosmic time was different. In the early days, stars formed faster, galaxies collided more often, and everything happened on a more compressed timescale. Fast forward to today, and the universe is vastly older, larger, and cooler. The rate of expansion has actually accelerated in recent billions of years due to a mysterious force known as dark energy. As galaxies drift apart, the rate at which the universe ages, in terms of entropy, structure, and change, is slowing down. You can think of time as having a kind of texture. In the early universe, it was turbulent, thick, and eventful. Today, it's more spread out, smooth, and calm. The pace of cosmic change is declining. In the far future, it may become nearly motionless. This brings us to a staggering realization. Time is not uniform across the history of the cosmos. It's not a metronome ticking at a fixed rate from beginning to end. It's more like a breathing organism, racing through its childhood, pacing in adulthood, and eventually settling into stillness in old age. So what happens next? Looking billions or even trillions of years into the future, we can predict several stages in the evolution of cosmic time. First, star formation will cease. Already, the rate of new stars being born is in decline. Eventually, galaxies will run out of the cold gas needed to form new stars. The night sky will go dark, one galaxy at a time. Then, stars will begin to die. The last red dwarfs, small, long-lived stars, will flicker out after trillions of years. White dwarfs will cool into black lumps of degenerate matter, called black dwarfs. Even the largest black holes will slowly evaporate via Hawking radiation, disappearing over unfathomable timescales, up to 100 years or more. At this stage, we enter the degenerate era, a period dominated by remnants, black dwarfs, neutron stars, and black holes. Time, in this era, becomes incredibly slow in a practical sense. With fewer events, fewer interactions, and minimal energy exchange, the clock of the universe ticks at a glacial pace. Eventually, we arrive at the heat death, the point at which the universe reaches maximum entropy. Matter will be evenly distributed. No more thermodynamic work will be possible. There will be no gradients of energy, no movement, no light. Just a thin haze of cold particles drifting in a flat, dark void. And here's the most haunting part. Time may become meaningless. Without change, there is no time. Time is a measure of difference, of before and after, of motion and transition. In a perfectly uniform, unchanging universe, there are no clocks to tick, no events to mark time's passage. Time would no longer be a useful or even valid concept, it would effectively stop. This fate, often called the Big Freeze, isn't just speculative. It's the logical conclusion of the laws of thermodynamics and current observations of dark energy. If nothing intervenes, this is the final destiny of time as we know it, a slow fading, a final stillness. Of course, we don't know for sure that this is the end. Other possibilities exist. The universe might cycle through expansions and contractions in a grand bounce. New physics might emerge. Or perhaps quantum fluctuations will birth entirely new universes, each with its own timeline, its own arrow of time. Some cosmologists even suggest that time itself might reverse in a far future epoch, an idea tied to exotic interpretations of entropy and symmetry. If that were the case, the final tick of our universe could be the first tick of another. These are extreme possibilities, but they all share one lesson. Time is not a passive backdrop. It is part of the universe's story. It evolves. It accelerates and decelerates. It is sculpted by energy, gravity, and entropy, and it may one day fade into silence. In the next part, we'll explore time travel, not just as science fiction, but as a serious concept in physics. Because as strange as time is, some of the math suggests we might be able to bend it, maybe even loop it. The question isn't just whether time moves, it's whether we can move through it. Time travel isn't just for science fiction anymore. While flying DeLoreans and phone booths may be fun on screen, physicists have spent decades seriously exploring whether time travel could be possible under the laws of physics as we currently understand them. The surprising answer: the equations don't rule it out. In fact, some solutions to Einstein's general relativity require time loops. But before we get too excited, let's break down what's really at stake. Let's begin with the basics. In the theory of special relativity, time travel to the future is not only possible, it's proven. When an object moves close to the speed of light, time slows down for it relative to a stationary observer. This is called time dilation, and it's not hypothetical. It's measured every day with satellites, particle accelerators, and high-precision clocks. If you were to travel at 99.999% the speed of light in a spacecraft for what felt like 1 year to you, you could return to Earth to find that centuries had passed. From your perspective, you'd have leapt into the future. This is a form of time travel that's entirely compatible with modern physics. But what about traveling to the past? This is where things get weird. According to general relativity, gravity isn't a force in the traditional sense. It's the warping of space-time by mass and energy. And under certain extreme conditions, that warping can create loops in space-time called closed time-like curves, CTCs. If these curves exist, they could allow for paths through the fabric of the universe that return to the same point in space and time. In 1949, Kurt Gödel, yes, the same Gödel famous for his incompleteness theorems, discovered a solution to Einstein's field equations that described a rotating universe. In this spinning cosmos, closed time-like curves naturally arise, meaning you could travel into your own past just by moving in the right direction. Later, physicist Frank Tipler proposed the idea of a Tipler cylinder, a massive, infinitely long, rapidly rotating cylinder of dense matter. If you traveled around it in a precise path, you could theoretically arrive before you left. Other proposals involve wormholes, tunnels through space-time connecting two distant points, potentially at different times. In 1988, Kip Thorne and colleagues showed that under specific conditions, a wormhole could be used for time travel. You'd need to stabilize it with exotic matter, something with negative energy density, which isn't known to exist in large quantities, but is theoretically possible in quantum field theory. So in theory, time travel to the past might not violate the laws of physics. But that doesn't mean it's practical, or even allowed in reality. For one thing, all known solutions to Einstein's equations that permit closed time-like curves rely on idealized, often impossible conditions. Infinite mass, perfect symmetry, or negative energy that may not exist. Then there's the issue of paradoxes. The most famous is the grandfather paradox. Suppose you travel back in time and prevent your grandfather from meeting your grandmother, then you would never be born, and therefore couldn't go back in time to stop them. The timeline collapses in on itself. To address this, some physicists have proposed that paradoxes are impossible in a self-consistent universe. According to the Novikov self-consistency principle, any action you take in the past must be consistent with the present you came from. If you travel back in time, you already did. Your presence was always part of history. You can't change anything because your actions are already woven into the timeline. In this view, the past is fixed, and time travel doesn't create paradoxes. It just fills in the blanks of what always happened. You can't kill your grandfather because somehow you never did. Other theories take a different approach, the multiverse. According to some interpretations of quantum mechanics, particularly the many worlds interpretation, every possible outcome of every event branches off into a separate timeline. So if you go back in time and change something, you don't alter your own timeline, you create a new one. Your original world continues as if nothing happened, while the new branch unfolds along a different path. This could allow for paradox-free time travel, but it also implies that you can't actually return to your original timeline. Once you change the past, you're in a different universe. Even if the physics allows time travel, there's a further problem: stability. Calculations show that time machines, especially those involving wormholes, may be inherently unstable. Quantum effects could create feedback loops that destroy the time machine the moment it's used. This is sometimes called the chronology protection conjecture, a term coined by Stephen Hawking. According to this idea, the laws of physics somehow conspire to prevent closed time-like curves from forming in the real universe, even if they're mathematically possible. So far, we haven't observed anything resembling a time traveler from the future, or a time machine in action. That could be because they're impossible, or it could be because any form of backward time travel is confined to the microscopic scale, limited to virtual particles in quantum loops, or effects that average out before they reach our macroscopic world. Still, the possibility remains tantalizing. Time travel stretches our understanding of causality, determinism, and the very structure of reality. Even if we never build a time machine, studying the conditions that allow, or forbid them, teaches us something profound. Time is not the rigid, linear force we imagine it to be. It is flexible, subject to geometry and energy, and maybe even choice. The deeper we explore time travel, the more we're forced to accept that our everyday experience of past leading to present, leading to future, might be only one facet of a far richer temporal reality. In the next part, we'll explore how time behaves near one of the most extreme objects in the universe, black holes. Because when it comes to warping time, nothing does it better or weirder than a black hole. If you want to see time stretched, slowed, and nearly torn apart, there's no better laboratory than a black hole. These enigmatic regions of space-time don't just bend gravity, they bend time itself. In fact, near a black hole, time begins to lose all meaning as it behaves in ways that defy our deepest intuitions. Let's start with what a black hole is. At its core, a black hole is a region where gravity is so intense that nothing, not even light, can escape. This escape boundary is known as the event horizon. Once you pass it, there's no turning back. But what happens as you approach the event horizon is where things get interesting, especially for time. According to general relativity, the presence of mass and energy warps space-time. The more massive and compact an object is, the more it curves the space and time around it. A black hole represents the most extreme version of this curvature. Its gravitational field is so strong that it dramatically slows down the passage of time in its vicinity. This effect is called gravitational time dilation. Imagine you're watching a spaceship slowly descend toward a black hole. As it gets closer to the event horizon, the ship appears to slow down. Its clock ticks more and more slowly relative to yours. Eventually, it seems to freeze at the edge, its image smeared and red-shifted, never quite falling in. From your perspective, outside the black hole, the spaceship never crosses the event horizon. But from the ship's own perspective, it plunges through in finite time, experiencing no strange effects at the horizon itself. This disconnect is one of the many bizarre ways time behaves near black holes. Now, let's imagine you are the one falling in. As you pass the event horizon, something strange happens. The roles of time and space begin to switch. Outside the black hole, time is the direction in which things change, and space is what you move through. Inside the event horizon, space becomes time. The singularity at the center isn't just in space, it's in your future. You're drawn toward it as inevitably as tomorrow. No amount of rocket power or maneuvering will save you. Inside the horizon, every path you can take leads you closer to the singularity. It's not just a place in space, it's a moment in time. A moment you are destined to reach, no matter what. This reversal of roles breaks our mental model of the universe. We think of time as a background, something separate from the landscape we move through. But a black hole proves otherwise. Time is the landscape, and in extreme gravitational fields, it can twist, stretch, freeze, and even fold in on itself. The strangest place of all may be the singularity at the heart of the black hole. According to Einstein's equations, it's a point of infinite curvature and density where the laws of physics break down. Time, as we know it, ceases to exist. But physicists suspect that singularities are a sign that our current theories are incomplete. To truly understand what happens there, we need a theory of quantum gravity. One of the leading ideas is that black holes are not singular points but quantum structures, perhaps loops of space-time or strings vibrating in higher dimensions. Some theories suggest that what looks like a singularity is actually a gateway to another region of the universe, or even another universe entirely. Wormholes, hypothetical tunnels through space-time, have been proposed as possible structures inside black holes. If such wormholes exist and remain stable, a big if, they could allow shortcuts through space and maybe even time. However, the conditions needed to keep a wormhole open would require exotic matter with negative energy, something we've never observed on a usable scale. Another idea gaining traction is the black hole firewall paradox, which challenges what happens at the event horizon itself. Some theories argue that an infalling observer would encounter a wall of high-energy particles at the horizon, effectively being incinerated instantly, rather than smoothly passing through. This would violate Einstein's equivalence principle and suggest that something deeper is going on at the intersection of gravity, time, and quantum mechanics. Then there's the infamous information paradox. According to quantum theory, information cannot be destroyed. But if matter falls into a black hole, and the black hole eventually evaporates via Hawking radiation, where does that information go? Is it lost forever, or is it somehow encoded in the radiation that escapes? Stephen Hawking himself revised his stance on this, eventually agreeing that information might be preserved at the edge of the black hole, in the form of a holographic surface. This leads us to the idea that the three-dimensional volume of a black hole, and possibly the universe, is encoded on a two-dimensional boundary, a notion tied to the holographic principle. In all of these theories, time plays a central role, not just as a passive dimension, but as an active participant in the structure of reality. Black holes aren't just fascinating because of their mass. They're laboratories for time itself. They show us what happens when time is stretched to its limits, slowed to a crawl, or warped beyond recognition. Here's the wildest part. Time dilation near black holes is so extreme that it could, in theory, allow a form of forward time travel. If you could orbit a supermassive black hole at just the right distance, say, the one at the center of our galaxy, you could experience hours while thousands of years pass for everyone else. When you return, the world would be unrecognizably different. You would have leapt into the future using nothing more than gravity. So while black holes may seem like dead ends, they could actually be windows, portals not only into deep space but deep time. And in studying them, we're forced to admit a fundamental truth. Time is not fixed. It is flexible, sensitive to motion and mass. And in the heart of a black hole, it begins to unravel. In the next part, we'll examine how the quantum world treats time, not as a flowing river, but as something even more elusive. Because at the smallest scales, time might not exist at all. At the cosmic scale, black holes stretch and warp time. But when we zoom into the smallest scales, the quantum realm, time becomes even stranger. The classical concept of time as a smooth, continuous flow breaks down. Instead, physicists encounter a murky and puzzling picture where time may lose its very meaning. Quantum mechanics, the theory describing the behavior of particles on atomic and subatomic scales, operates with probabilities rather than certainties. In this realm, particles exist in superpositions, being in multiple states simultaneously, and events don't follow a strict cause-effect chain like in classical physics. But what about time itself? Unlike space, time in quantum mechanics has always been treated differently. Time is typically an external parameter, a backdrop against which particles evolve. The famous Schrödinger equation describes how the quantum state of a system changes over time, but time itself is not quantized or uncertain. It's just a parameter we measure things against. This treatment, however, is problematic when we try to combine quantum mechanics with general relativity, the theory of gravity and space-time. In relativity, time is dynamic and linked with space, but in quantum mechanics, it's a fixed, absolute parameter. This inconsistency is at the heart of the problem known as quantum gravity. Several approaches aim to reconcile these views. Some, like loop quantum gravity, attempt to quantize space-time itself, suggesting that space and time have a discrete structure at the Planck scale, about 1035 meters and 1043 seconds. In these models, time doesn't flow smoothly, but comes in tiny ticks, like pixels on a screen. Other approaches, like string theory, incorporate time as one dimension within higher dimensional space, but they also struggle with making time fully compatible with quantum uncertainty. One of the most radical ideas is the timeless or background-independent approach. Here, time is not fundamental, but emerges from the relationships between quantum states. Instead of time driving change, change defines time. Imagine a complex dance where dancers move relative to each other, but without an external clock. Observers inside the dance can measure how dancers shift positions and infer a sense of time. But outside the dance, there is no ticking clock. This relational view suggests that time arises only because systems have correlations. Without interactions or change, time has no meaning. Another quantum puzzle is entanglement, where particles remain connected no matter how far apart they are, instantly affecting each other's states. This phenomenon seems to violate classical notions of causality and temporal order, further complicating time's role. The famous Wheeler-DeWitt equation, a candidate for the quantum gravity wave function of the universe, does not contain time explicitly. It describes the universe's entire quantum state as a whole, timeless entity. This frozen formalism challenges our idea that the universe is constantly evolving through time. How do we reconcile this with the obvious fact that we experience time passing? One answer lies in decoherence. When quantum systems interact with their environment, superpositions collapse into definite states, creating a classical world where time's flow appears real. Our conscious experience of time may emerge from this transition from quantum timelessness to classical temporality. The interplay between quantum uncertainty, relativity, and time remains one of the greatest mysteries in physics. Some speculate that resolving it will require a radical new framework, one that redefines time not as a dimension, but as an emergent phenomenon born from information, entropy, and quantum entanglement. If that's true, then our everyday experience of seconds ticking by is just a shadow of a deeper, more complex reality. A reality where time is fluid, fragile, and perhaps not fundamental at all. In the next part, we'll explore how this strange nature of time influences the very concept of causality, and what it means for our understanding of free will and determinism. Time and causality have always been intertwined. We understand cause and effect as a chain unfolding through time. A causes B, which leads to C. This intuitive flow underpins science, philosophy, and our everyday lives. But if time isn't the straightforward river we imagine, what does that mean for causality and for the idea of free will? At its core, causality means that causes precede their effects. The past influences the present, which influences the future. Without this order, prediction and explanation break down. Yet, as we've seen, physics at its deepest levels challenges the simplicity of temporal ordering. In relativity, the sequence of events depends on the observer's frame of reference. Two observers moving at different speeds can disagree about which event came first. Causality is preserved only if signals and influences don't travel faster than light, ensuring that cause-effect relationships remain consistent within each observer's light cone. But quantum mechanics adds more puzzles. In quantum entanglement, two particles share a connection so immediate that measuring one instantaneously affects the other, even if separated by vast distances. This phenomenon, famously called spooky action at a distance by Einstein, seems to challenge classical causality because it doesn't rely on any signal traveling through space or time. Yet, experiments confirm that entanglement does not allow faster-than-light communication, preserving causality's core principle. Instead, it suggests that our classical notions of locality and causality need refinement. If time itself is emergent, then cause and effect may not be fundamental either. Some physicists propose that causality arises from the ordering of events embedded in the quantum fabric, a network of correlations rather than a linear timeline. This opens up questions about determinism. If cause and effect are emergent and time is flexible, are our choices predetermined, or is there room for genuine free will? Classical determinism, the idea that every event follows inevitably from prior conditions, rests on the assumption of a fixed timeline. But quantum indeterminacy introduces fundamental randomness at microscopic scales. Some interpret this randomness as a source of free will, while others see it as simply unpredictability. Philosophers debate whether randomness alone can produce meaningful free will. After all, a choice made by chance is not truly free in a conscious, intentional sense. More nuanced views suggest that free will could emerge from complex systems, like the brain, interacting with an open, probabilistic universe where time and causality are flexible. The block universe model we discussed earlier challenges free will even further. If past, present, and future coexist in a fixed space-time, is there any room to change the future? Or are all our decisions already etched into the cosmic block? Some argue that this is compatible with a deterministic universe where free will is an illusion. Others propose compatibilist views, where free will and determinism coexist because freedom is about acting according to one's desires, regardless of cosmic predestination. The multiverse perspective offers another angle. If every possible outcome occurs in some branch of reality, then every choice you make exists somewhere. This could reconcile free will with a deterministic structure. Every decision splits reality into alternatives. At the intersection of time, causality, and consciousness, science still faces profound mysteries. How do we reconcile our felt experience of making choices with the apparent rigidity or randomness of the universe? Does time's strange nature give space for agency or constrain it? Understanding time's true nature might reshape philosophy and ethics as much as physics. After all, how we view time shapes how we think about responsibility, morality, and the meaning of our lives. In the next part, we'll explore how time influences our biological clocks, how living organisms measure, adapt to, and even manipulate time in astonishing ways. From the vast cosmos to the microscopic quantum realm, we've explored how time bends, warps, and sometimes disappears. But what about here on Earth, inside living beings? How does time affect biology, and how do organisms experience and manage time? Life is deeply intertwined with time. Our bodies run on cycles, daily, seasonal, and even yearly rhythms that regulate everything from sleep and metabolism to reproduction and growth. These biological clocks are essential for survival, finely tuned through millions of years of evolution. At the heart of this system are circadian rhythms, roughly 24-hour cycles driven by internal molecular clocks. These clocks synchronize with the external environment, especially the cycle of light and dark. The master clock in humans is located in a tiny region of the brain called the suprachiasmatic nucleus, SCN. It processes light signals from the eyes and orchestrates the timing of hormonal release, body temperature, and behavior. But why do organisms have these internal clocks at all? Timekeeping provides a huge evolutionary advantage. By anticipating daily changes, like sunrise and sunset, animals can optimize feeding, mating, and rest. Plants open their leaves to catch sunlight during the day and close them at night. Migratory birds time their journeys to coincide with favorable weather and food availability. Interestingly, circadian rhythms persist even in constant conditions, like total darkness, showing that these clocks are intrinsic rather than mere responses to the environment. Beyond circadian rhythms, organisms have ultradian cycles, shorter than 24 hours, like heartbeats and breathing, and infradian rhythms, longer than 24 hours, such as menstrual cycles and seasonal behaviors. At the cellular level, molecular feedback loops regulate these rhythms with remarkable precision. Genes switch on and off in cycles, producing proteins that in turn regulate gene expression, forming biological oscillators that keep time. The concept of chronobiology, the study of biological timing, is revealing that time is embedded deep in life's fabric. Humans also perceive time subjectively. Our experience of time's passage varies with mood, attention, and age. When we're engaged or excited, time seems to fly. When bored or anxious, it drags. Neuroscientists link this to brain regions like the basal ganglia and the cerebellum, which process temporal information. Our brain constructs time through complex networks, integrating sensory inputs and memory. This means our perception of time is malleable and can be distorted by emotions, drugs, or neurological conditions. Interestingly, some animals have extraordinary time perception. For example, flies have extremely fast visual processing, allowing them to react in milliseconds, essentially perceiving time in slow motion compared to humans. On longer scales, certain species track seasonal time with incredible accuracy. Arctic animals can anticipate changes in daylight and food availability, triggering migration or hibernation precisely. Even plants show complex temporal behavior. The famous sensitive plant closes its leaves in response to touch, but this response can be modulated by circadian cycles, linking mechanical stimuli with time. Humans have developed cultural tools to measure and organize time externally: calendars, clocks, rituals, reflecting our desire to control and harness this elusive dimension. But what about manipulating time biologically? Research into time perception and time dilation at the cognitive level is ongoing. Meditation, hypnosis, and certain drugs can alter how we experience time, revealing that subjective time is flexible. On a molecular level, some studies suggest that slowing down biological aging, the biological clock, could extend lifespan. Telomeres, protective caps on chromosomes, shorten with time and cellular replication, and their maintenance is linked to aging. If we understand how biological time works, could we extend or modify it? Could we biologically hack time to live longer or change our perception of it? These questions sit at the boundary of biology, psychology, and philosophy. Ultimately, life itself is a dance with time, a balancing act of rhythms and cycles that synchronize us to the universe's temporal flow. While time may be strange and elusive at the cosmic scale, here on Earth it beats steadily in every cell and heartbeat, shaping all living experience. In the next part, we'll dive into how human cultures across history have understood and represented time, from ancient calendars to modern physics. Since the dawn of human civilization, our relationship with time has been both practical and profound. Cultures around the world have sought to understand, measure, and represent time, often blending observation, mythology, and ritual. In this part, we explore how humans have conceptualized time throughout history, setting the stage for the scientific revolutions that changed everything. Early humans experienced time through natural cycles: the rising and setting of the sun, the phases of the moon, the changing seasons. These rhythms shaped hunting, planting, and migration. Observing these cycles gave rise to the first calendars, systems that helped predict important events, like floods or harvests. One of the oldest known calendars is the lunar calendar, based on the moon's phases. Ancient civilizations like the Babylonians, Egyptians, and Mayans developed increasingly sophisticated calendars, incorporating solar and lunar cycles. The Egyptians famously built the obelisks and pyramids aligned to celestial events, indicating an advanced understanding of astronomy and time. Time was often intertwined with religious and mythological beliefs. Many cultures viewed time as cyclical, an endless loop of birth, death, and rebirth. The Hindu concept of kalpas envisions vast cycles lasting billions of years. The ancient Greeks saw time in terms of chronos, sequential, measurable time, and kairos, the opportune moment, distinguishing between quantitative and qualitative time. In contrast, the Judeo-Christian tradition often depicts time as linear, a creation with a beginning, progressing toward an ultimate end or divine purpose. The invention of mechanical clocks in medieval Europe revolutionized timekeeping. For the first time, people could measure hours, minutes, and seconds independently of the sun's position. This development transformed society, enabling precise scheduling and coordination in commerce, science, and daily life. The scientific revolution brought deeper insights. Isaac Newton introduced the concept of absolute time, an unchanging, universal clock ticking uniformly for all observers. Time was a backdrop against which events unfolded, independent of anything else. Newtonian time fit everyday experience and worked well for centuries, but it ran into problems with electromagnetism and the speed of light. Enter Albert Einstein. His theories of special and general relativity shattered the notion of absolute time. Time became relative, depending on the observer's velocity and gravitational field. There was no universal now. Instead, each observer experienced their own flow of time. This was a radical shift, challenging not just physics, but philosophy itself. Time was no longer a fixed container, but a dynamic player in the universe's fabric. The 20th century also saw quantum mechanics add complexity, treating time differently from space and hinting at its emergent nature. Meanwhile, in philosophy and psychology, thinkers explored time's subjective and existential dimensions. Henri Bergson distinguished between mathematical time and lived time, emphasizing duration and experience over measurable units. Literature and art have long grappled with time's fluidity. From Marcel Proust's explorations of memory to Jorge Luis Borges's labyrinthine stories, time becomes a malleable narrative device reflecting human consciousness. In modern culture, time dominates our lives more than ever, measured by atomic clocks with incredible precision, compressed by digital technology, and experienced in faster-than-ever rhythms. Yet, despite this precision, our experience of time remains deeply personal and mysterious. Understanding the cultural history of time reveals how humans have struggled to reconcile the measurable and the meaningful, the cosmic and the intimate. From ancient calendars to Einstein's space-time, time is both a scientific concept and a human story. In the next part, we'll journey into the future of time measurement, looking at atomic clocks, quantum clocks, and how technology is pushing the boundaries of what we can detect and manipulate. From ancient sundials to the ticking of grandfather clocks, humanity's quest to measure time has evolved dramatically. Today, we stand at the cutting edge of precision timing, where atomic clocks and emerging quantum technologies redefine what it means to track time. In this part, we'll explore how our instruments have transformed time from an abstract concept into an exact science, and how new frontiers might soon allow us to manipulate time itself. The journey toward precise timekeeping accelerated dramatically in the 20th century. The invention of the quartz clock in the 1920s was a milestone. By harnessing the steady vibration of quartz crystals under electrical excitation, scientists created clocks far more accurate than any mechanical predecessor. This allowed timing to improve from seconds lost per day to milliseconds or less. Yet quartz technology soon gave way to something even more precise: the atomic clock. Atomic clocks operate on the principle that atoms, like cesium or rubidium, absorb and emit electromagnetic radiation at very specific frequencies when their electrons change energy states. These frequencies are consistent across all atoms of the same element, making them ideal ticks for clocks. In 1967, the International System of Units, SI, redefined the second based on the cesium-133 atom's transition frequency, 9,192,631,770 cycles per second. This definition grounded time measurement in unchanging quantum properties, making it universal and stable. Today's cesium atomic clocks are astonishingly precise, losing less than 1 second over millions of years. They underpin technologies critical to modern life: GPS navigation, telecommunications, and network synchronization. But even atomic clocks are being surpassed. The latest innovations are optical lattice clocks and quantum clocks that use lasers to trap atoms and measure frequencies at optical, light, rather than microwave wavelengths. These clocks are so accurate they could lose or gain less than a second over the entire age of the universe. What's the significance of such precision? First, it allows scientists to test fundamental physics with unprecedented accuracy. For example, by comparing clocks at different gravitational potentials, such as at varying altitudes, we can observe gravitational time dilation directly. Experiments confirm Einstein's predictions to extraordinary precision, further validating general relativity. Second, ultra-precise clocks enable advances in technology and industry. Enhanced GPS accuracy improves everything from navigation to earthquake monitoring. Financial markets rely on tightly synchronized timestamps. Deep space communications require timing precision to coordinate signals across billions of kilometers. Moreover, by monitoring subtle changes in clock rates, researchers can detect potential variations in fundamental constants of nature, offering clues to new physics beyond the standard model. Looking ahead, scientists are investigating how to harness quantum entanglement and superposition to develop even more precise timekeeping devices. Quantum clocks could push accuracy further by reducing noise and uncertainty inherent in measurements. Another exciting avenue involves nuclear clocks, which would use transitions within atomic nuclei rather than electrons. Because nuclear energy levels are less affected by environmental disturbances, nuclear clocks could redefine precision even beyond optical clocks. But what if measuring time precisely is just the beginning? Some theorists speculate that future technologies might manipulate time, or at least its flow, by controlling quantum states or gravitational fields. For example, controlled manipulation of time dilation through velocity or gravity could, in principle, allow travelers to experience time at different rates, as predicted by relativity. Although such scenarios are currently impractical, advances in propulsion or gravitational engineering might one day make them conceivable. Even more speculative are ideas about engineering quantum states to influence the direction of time or exploit temporal correlations in entangled systems for communication or computation. Beyond technology, pushing the limits of time measurement challenges our understanding of reality. If time is emergent and flexible, as many theories suggest, then our instruments become tools not just for tracking time, but for probing the fundamental nature of space-time itself. This frontier is rich with philosophical implications. Is there a limit to how finely time can be measured? Does time have a discrete structure at the smallest scales? Or is it continuous? Could we discover phenomena that cause the arrow of time to reverse or pause? In sum, humanity's quest to measure and understand time has transformed it from a vague notion to an exact science that touches every aspect of modern life. Yet, as we develop ever more precise clocks and explore quantum and gravitational realms, we uncover deeper mysteries that challenge our most basic assumptions. Time, it seems, is not merely a dimension to be measured. It is a dynamic fabric intertwined with the universe's deepest secrets. In the next part, we'll explore the profound concept of the arrow of time, why time seems to flow in one direction, and what that means for the universe. One of the most puzzling features of time is its apparent directionality. The fact that it seems to flow forward, from past to future, and never the other way around. This phenomenon is known as the arrow of time. But why does time have an arrow? And why is the future so different from the past? At the fundamental level, the laws of physics, especially those governing fundamental particles and forces, are mostly time-symmetric. That means if you reverse the flow of time in the equations, the processes would still be physically possible. A video of two colliding billiard balls looks just as natural, played forwards or backwards. Yet our everyday experience couldn't be more different. We see eggs breaking but never spontaneously reassembling. Heat flows from hot to cold, never the reverse. We remember the past but not the future. This irreversible progression is the essence of the arrow of time. The key to understanding this lies in thermodynamics, the physics of heat, energy, and disorder. The second law of thermodynamics states that entropy, a measure of disorder, tends to increase in a closed system. In other words, the universe moves from states of low entropy, order, to high entropy, disorder. This increase in entropy sets the thermodynamic arrow of time. It provides a direction to time, from ordered past to disordered future. Once a glass shatters, its entropy increases. Spontaneous reversal to a perfect glass would require a decrease in entropy, which is incredibly improbable. But why was the early universe in a low entropy state to begin with? This remains one of the greatest mysteries in cosmology. The Big Bang's initial conditions were remarkably ordered, setting the stage for entropy to increase and time's arrow to emerge. Other arrows of time have been proposed. The psychological arrow corresponds to our perception of time flowing and the asymmetry between memory of the past and ignorance of the future. The cosmological arrow points in the direction of the universe's expansion. Interestingly, these arrows are linked. The expansion of the universe creates conditions for entropy to increase, which shapes our psychological experience of time. At the quantum scale, the arrow of time is less clear. Quantum processes can be reversible, and the role of entropy is subtle. Recent research explores how quantum decoherence, the interaction of quantum systems with their environment, might give rise to effective irreversibility and the emergence of classical time's arrow. Philosophers and physicists debate whether the arrow of time is fundamental or emergent. Is the flow of time an illusion created by entropy's increase, or is it a basic property of the universe? If entropy defines time's arrow, what happens in a hypothetical universe where entropy decreases? Would time flow backward? Could we remember the future and not the past? Some speculative cosmological models suggest that if the universe were to contract instead of expand, the arrow of time might reverse. This raises mind-bending possibilities about causality and experience. The arrow of time is deeply connected to the very meaning of existence. It underpins the concepts of cause and effect, memory, and change. Without a direction to time, life as we know it, rooted in growth, decay, and learning, would be impossible. Ultimately, the arrow of time is a bridge between physics and consciousness. Understanding it could unlock answers to why the universe is the way it is and how we fit into the cosmic flow. In the next part, we'll explore time and information, how the universe processes, stores, and erases information, and what this means for time itself. Information and time are deeply intertwined concepts, perhaps two sides of the same cosmic coin. To understand how time really works, we must explore how the universe processes, stores, and transforms information. In physics, information is not just data or knowledge, it's a fundamental physical quantity. The famous physicist John Archibald Wheeler coined the phrase "it from bit," suggesting that information underlies every physical phenomenon. Matter, energy, and space-time itself emerge from information at a fundamental level. One way to grasp the connection between time and information is through entropy. Entropy is often described as disorder, but more precisely, it's a measure of missing information about a system's microscopic state. The more disordered a system appears, the less information we have about its precise configuration. The second law of thermodynamics, which drives the arrow of time, states that entropy tends to increase, meaning information about the universe's exact microstates becomes more hidden over time. As entropy grows, the universe's information becomes more scrambled, and this scrambling is irreversible. This irreversible loss, or rather dispersal, of usable information is what gives time its forward direction. Once information spreads into the environment, reconstructing the past becomes impossible, cementing causality and temporal order. Black holes provide a fascinating twist on the information-time link. According to Stephen Hawking, black holes emit radiation and can eventually evaporate, seemingly destroying information about the matter that fell into them. This information paradox challenges the idea that information is conserved. Modern theories suggest that black hole information is not lost but encoded on the event horizon surface, a concept called the holographic principle. This idea implies that the universe itself might be a vast hologram, where three-dimensional information is stored on two-dimensional boundaries. If true, This radically changes our understanding of space, time, and reality. Information theory also plays a crucial role in quantum mechanics. Quantum states carry information that can be entangled, superposed, and measured, but not copied or destroyed, a principle known as the no-cloning theorem. Quantum information behaves very differently from classical information, influencing time's nature on microscopic scales. Moreover, the Landauer principle states that erasing one bit of information in a physical system requires a minimum amount of energy, linking information, thermodynamics, and time. This connection suggests that time's flow might be linked to the processing and erasure of information, physical acts that require energy and generate entropy. In biological systems, information processing underpins life and consciousness. Our brains constantly encode, store, and retrieve information, creating memories that shape our subjective experience of time. Some theorists propose that consciousness and the flow of time emerge from the way information is processed within complex systems. The brain's neural networks integrate information over time, constructing a coherent sense of past, present, and future. Advances in quantum computing and information science may one day allow us to probe these connections more deeply. Could manipulating quantum information alter the flow of time or consciousness? Could we create systems that experience time differently? In summary, information is a foundational thread weaving through the fabric of time. The universe's evolution, the arrow of time, black holes, quantum mechanics, and even consciousness itself may be expressions of how information is handled and transformed. Understanding this link brings us closer to unraveling the ultimate nature of time, a journey that bridges physics, computation, and philosophy. In the next part, we'll examine the role of time in cosmology, how time began, how it might end, and what the universe's fate tells us about time's nature. The story of time is inextricably linked to the story of the universe itself. To understand time at the deepest level, we must examine its origins, evolution, and possible ends through the lens of cosmology, the study of the universe as a whole. Where did time begin? According to the prevailing Big Bang theory, time and space emerged together about 13.8 billion years ago, in an event that marked the birth of our universe. Before this event, the conventional concept of time, measured as before and after, may not have existed at all. In general relativity, space and time are woven into a four-dimensional fabric called space-time. The Big Bang corresponds not just to a moment in time, but to the creation of space-time itself. Asking what happened before the Big Bang is complicated because without space-time, the notion of before may be meaningless. This idea revolutionizes our understanding of time. Time is not an absolute background. It has a beginning tied to the universe's expansion. However, some cosmological models suggest alternatives. For example, in cyclic or bounce cosmologies, the universe undergoes endless cycles of expansion and contraction. Time, in these models, may be eternal, with no absolute beginning or end, but instead repeating phases. Others explore multiverse scenarios where our universe is one of many, each with its own space-time and possibly different laws of physics and time behavior. The flow of time in the expanding universe. Since the Big Bang, the universe has been expanding, causing galaxies to drift apart. This expansion affects how time behaves on cosmic scales. Because of the universe's expansion, light from distant galaxies is redshifted, its wavelength stretched. The further we look, the further back in time we see. This cosmic timescale lets astronomers peer deep into the past, observing the early universe and how time and space evolved. Moreover, the universe's expansion affects gravitational fields and thus the flow of time. Near massive clusters, time runs slower than in vast cosmic voids. This interplay between gravity, expansion, and time is fundamental to cosmology. The ultimate fate of time and the universe. What does the future hold for time? Cosmologists propose several scenarios depending on the universe's density, dark energy behavior, and other factors. The Big Freeze, heat death, the most widely accepted outcome is that the universe will keep expanding forever. Over trillions of years, stars burn out, galaxies drift apart, and the cosmos becomes cold and dark. As entropy maximizes, all processes slow and eventually stop. Time will continue, but the universe will approach a timeless, lifeless equilibrium. The Big Crunch. In a denser universe, gravity might eventually halt and reverse the expansion, causing everything to collapse back into a hot, dense state. Time, in this scenario, would approach an end similar to its beginning. However, current data suggests this scenario is unlikely. The Big Rip. If dark energy grows stronger over time, it could tear apart galaxies, stars, planets, and even atoms. This violent end would disrupt space-time itself. Time as we know it could cease in such extreme conditions. Quantum bounce or multiverse transitions. Some theories propose that the end of one universe triggers the birth of another, perhaps via quantum fluctuations or other mechanisms, leading to an eternal cosmic cycle where time is infinite but local. Time and cosmic horizons. Our observable universe is limited by the cosmic horizon. The maximum distance light has traveled since the Big Bang. Beyond this horizon, regions of space are causally disconnected from us. We can never observe or interact with them. This horizon imposes a boundary on the flow of time as experienced by observers. Different observers in different regions may have different cosmic horizons and effectively different time domains. This raises profound questions. Does time exist beyond our observable universe? Is time an absolute cosmic property or observer-dependent? Modern cosmology struggles to reconcile these questions with relativity and quantum physics. Time before the Big Bang. While classical general relativity breaks down at the singularity, quantum gravity attempts to describe what happened at, or before, the Big Bang. Loop quantum cosmology replaces the singularity with a quantum bounce, where a prior contracting universe transitions into our expanding one. In this model, time extends before the Big Bang, but behaves differently, possibly losing its classical meaning. String theory and other approaches suggest that time could be emergent, or that there might be multiple time dimensions hidden from our perception. All these models challenge the classical intuition that time has a simple, linear origin. Time and the initial conditions. Why did the universe begin in such a low entropy, ordered state? This remains a deep mystery. Some theories invoke the anthropic principle, suggesting that only universes with such conditions can support observers like us. Others propose a multiverse where all initial conditions exist, but we inhabit a rare, hospitable bubble. Understanding these initial conditions is critical for grasping the nature of time's arrow and the universe's evolution. Cosmic time and human time. The cosmic scale of time dwarfs human experience. Billions of years unfold as a single cosmic breath. Yet we find meaning and structure by connecting our brief lives to this vast temporal tapestry. Cosmology teaches us that time is not universal or absolute, but intertwined with space, gravity, and the universe's fate. It invites us to rethink time as a dynamic, evolving dimension shaped by the cosmos itself. At this stage in our exploration, we've seen time stretch and bend near black holes, fade and emerge in quantum realms, and expand alongside the cosmos itself. Now we delve into one of the most enigmatic and profound aspects of time, its relationship with consciousness and memory. How does our mind experience time? Is our perception of past, present, and future an illusion or a fundamental aspect of reality? Human consciousness experiences time in a way that seems seamless and continuous. Yet neuroscience reveals that this experience is a constructed narrative, an ongoing integration of sensory input, memories, and predictions. The brain actively organizes events into temporal sequences, giving rise to the feeling of a flowing timeline. The neural basis of time perception. Time perception involves multiple brain areas, including the prefrontal cortex, cerebellum, basal ganglia, and hippocampus. These regions coordinate to estimate durations, sequence events, and encode memories. Experiments show that humans can estimate brief intervals, milliseconds to seconds, with surprising accuracy. However, this perception is influenced by attention, emotion, and context. For example, when we're bored or anxious, time may feel sluggish. When we're engaged or excited, it can speed by. This subjective malleability challenges the idea that time perception is a simple readout of a universal clock. Instead, our internal clock is plastic and depends on neural states, memory, and the construction of temporal reality. Memory plays a crucial role in how we construct our temporal reality. Episodic memory, the ability to recall personal past events, anchors us to a subjective past. Our brain stores not just facts, but the sequence and context of events, creating a timeline. Interestingly, the brain also simulates future events using similar neural circuits. This mental time travel allows planning, anticipation, and imagination. The same brain regions active during recalling past experiences fire when envisioning the future. This blurs the strict boundary between past and future in our experience, suggesting that temporal distinctions are deeply tied to cognition. The present moment, a temporal illusion. Philosophers and scientists debate the nature of the present moment. Is the now a fleeting instant, a small window, or an illusion? Neuroscience suggests that the brain integrates sensory information over brief time windows, hundreds of milliseconds, to create the experience of the present. This integration means that our now is slightly delayed relative to external events. Furthermore, some argue that the present is not an absolute slice of time, but a psychological construct shaped by memory and prediction. Disorders of time perception. Certain neurological conditions affect how individuals perceive time. For example, Parkinson's disease, which involves basal ganglia dysfunction, often impairs timing abilities. Schizophrenia and temporal lobe epilepsy can distort the sense of time's flow and temporal ordering of events. These disorders reveal how fragile and constructed our temporal experience is, reliant on complex neural processes. Time and consciousness, deeper mysteries. Philosophically, the connection between consciousness and time raises profound questions. Some argue that consciousness itself creates the flow of time, that without an observer, time has no meaning. Others propose that time and consciousness co-emerge from fundamental physical processes. As we stand on the threshold of a technological revolution, emerging fields like artificial intelligence, AI, and quantum computing promise to reshape not only how we process information, but also how we understand and manipulate time itself. This part explores how these cutting-edge technologies challenge and expand our relationship with time, opening new frontiers in science, philosophy, and daily life. Artificial intelligence and time perception. Artificial intelligence systems, especially those based on machine learning, operate on discrete data inputs and process sequences over time. While AI does not possess consciousness or subjective time experience, it is designed to handle temporal data, recognizing patterns across time, predicting future trends, and making decisions based on sequences. For example, natural language processing models analyze the order of words to comprehend meaning. Autonomous vehicles process sensory inputs in real time to navigate safely. One fascinating area is temporal reasoning, the ability of AI to understand causality, timelines, and event relationships. Advances here could lead to AI systems capable of more human-like planning, storytelling, and forecasting. In essence, AI is beginning to simulate aspects of time awareness, helping us model and predict complex temporal phenomena that challenge human cognition: quantum computing and time. Quantum computers harness superposition and entanglement to perform calculations that would be infeasible on classical machines. Because quantum states evolve according to the Schrödinger equation, a fundamentally time-dependent equation, quantum computing is intimately connected with the flow and manipulation of quantum time. Moreover, quantum algorithms often exploit interference effects that depend on precise timing and phase relationships. Quantum clocks, as discussed earlier, form the backbone of potential quantum timing devices, improving synchronization and precision. More speculatively, some researchers explore whether quantum computers could simulate aspects of space-time or even rewind quantum processes, hinting at future abilities to probe or manipulate time in unprecedented ways. Time in simulations and virtual worlds. Digital technologies increasingly create virtual realities and simulations where time can be controlled or distorted. In video games, time can be paused, slowed, or sped up, offering experiences impossible in the physical world. Researchers use simulations to model complex systems, from climate change to particle interactions, where controlling the time variable is essential to experimentation. As virtual environments grow more immersive, questions arise about subjective time in simulated consciousness. Could an AI or synthetic mind within a simulation experience time differently? Could time itself be manipulated as a resource? Technological impacts on human time experience. Technology changes how humans experience time daily. Instant communication compresses timelines. Social media accelerates information flow. 24/7 connectivity blurs boundaries between work and rest. Digital devices influence our attention, altering perceived duration and engagement. Additionally, biofeedback and wearable tech enable us to monitor and potentially modulate biological rhythms, impacting our internal clocks. In the future, brain-computer interfaces might alter temporal perception or allow new forms of temporal cognition. Philosophical and ethical questions. With growing technological power to measure and manipulate time comes ethical responsibility. If technologies could someday affect biological aging, memory, or consciousness, what would that mean for identity and society? Could altering subjective time lead to psychological risks or inequalities? Furthermore, as AI systems grow in temporal reasoning, how do we ensure alignment with human values over time, towards a new temporal paradigm? These technologies hint at a future where time is not merely measured or experienced passively, but actively shaped. The convergence of AI, quantum computing, neuroscience, and physics could yield new ways to understand time's fabric, perhaps even allowing limited control over its flow. Such advances may revolutionize everything from healthcare to communication, creativity, and exploration. Yet many mysteries remain. Time, elusive and multifaceted, resists simple mastery. Our journey through the nature of time reveals it as a dynamic interplay of physics, information, consciousness, and now technology, a dimension still full of wonder and discovery. As we conclude this exploration of time, a concept far stranger and more complex than everyday experience suggests, it's fitting to reflect on how this elusive dimension shapes our reality, challenges our understanding, and inspires future discovery. Throughout this journey, we've unraveled layers of time's mystery, from the warped space-time near black holes to the probabilistic pulses of quantum mechanics, from the ticking of atomic clocks to the deep time evolution of the cosmos, from the biological rhythms beating within us to the mental constructs that weave past, present, and future into coherent narrative. Time as a construct and a reality. One profound realization is that time is both an objective and subjective phenomenon. Physically, time is a dimension inseparable from space, malleable under gravity and velocity, and intimately connected to energy, matter, and information. Yet, psychologically, time is deeply personal, our perception sculpted by neural processes, memory, attention, and emotion. This duality challenges us to reconcile the block universe view, where past, present, and future coexist, with the flowing river of time we experience. Is time fundamentally static or dynamic? Are past and future real or emergent illusions? Modern physics and philosophy continue to debate these questions. Time's arrow and the flow of change. Entropy's inexorable increase gives time its arrow, shaping cause and effect and the sequence of events. Without this directionality, complexity, life, and consciousness would be impossible. Time's flow allows change, growth, decay, and evolution. Yet, at the smallest scales, time may lose this directionality, hinting that what we see as flow emerges from deeper, timeless laws. Information and time. Information links time, physics, and consciousness. The universe's evolution can be seen as information processing on the grandest scale. Our memories, decisions, and even awareness arise from complex information patterns evolving through time. The paradoxes of black holes and quantum information reveal that understanding time may be inseparable from understanding information's nature. Technological frontiers. Advances in atomic and quantum clocks, AI temporal reasoning, and brain-machine interfaces promise new ways to measure, experience, and perhaps influence time. These technologies carry both promise and ethical challenges, as we shape not only how we track time, but how we live within it. A journey without end. Ultimately, time remains one of the universe's deepest mysteries. Our best theories describe it as a flexible, emergent phenomenon woven into space-time's fabric and shaped by thermodynamics and quantum laws.